So this week we have Nan Jiang, who's going to be presenting work on the hardness of RL with value function approximation. Nan is an assistant professor of computer science at the University of Illinois. Prior to that, he was a postdoc at Microsoft New York and did his PhD at the University of Michigan, advised by Santander Singh. His research interests are in the theory of reinforcement learning, mostly focusing on sample efficiency. It's a great pleasure to have him here today. So over to you, Nan.
Thank you. I would like to thank Kara, Chava, and Gergo for organizing this wonderful event and having me here. So today I'll be talking about some results on batch value function approximation, which is based on an ISML paper last year, Information-Theoretic Considerations in batch RL. Okay, so for today, we'll be thinking about value function approximation, which means that we're going to use a restricted class of functions to approximate the optimal value function Q star, right? And we're assuming that we're in the batch learning mode, which means that we're passively given an exploratory data set, and I'll define exploratory in a few slides. And we do not have further access to the environment, okay? And if you think about this, right, so why do we want to understand batch VFA, right? So, well, one of the important reasons is because it helps us understand many popular deep RL algorithms, because although those algorithms have access to, have online access to the environment, they're really just combining some heuristic exploration mechanism with an off policy or batch RL algorithms, right? So you know, these environments, sometimes they're easy to explore, so you collect a exploratory data set, and really the really crucial part is that you want to have a value function approximation algorithm that works very well given a good data set, right? So the key question I'm going to focus today is, when can we guarantee sample efficient learning, right? So more precisely, what technical conditions do we need so that we can claim that we obtain polynomial sample complexity? Okay, so, and again, I'm gonna formalize that a bit, formalize it shortly. Okay, so before we dive into more details, I just want to give a little heads up of what this talk is going to be like, because it's going to be a little bit different from many of the talks you've heard. So first of all, I'll introduce no new algorithms, and I'll introduce many open problems. And I can tell you I have only solved a small portion of them. And I'll be talking a lot about hardness results or negative results or lower bounds in this talk to help us understand what conditions do we really need and what conditions we may not need. And sometimes when I fail to obtain a hardness result, I will give you something more terrible that is like doubly negative results. Okay, so why it is hard to prove certain hardness conjectures. And some of you might have seen a version of this talk, you know, from MSR or Simon's Institute. And today, because we have a dedicated RL theory audience and we have, you know, gone through many related topics in the past. So I think today I'll be able to dive much deeper into this paper and talk about some of the very interesting technical aspects which I've failed to cover in the previous talks. Okay, so let's really get started. Okay, so so what do I mean by sample efficiency, right? So what I want to do first is to anticipate what kind of results I'm looking for. Right, so here I'm drawing a comparison between supervised learning and reinforcement learning, right? So in supervised learning, what's the kind of you know, sample complexity result you learn in the day one of a learning theory course? Well, it's something like this, right? So you have a data set, which are XY pairs drawn from a joint distribution, and you have a class of predictors F, and let's assume there is a finite class. And one of the predictors gives you good predictions, right? So, and Y may be real valued or it may be, you know, binary labels, doesn't matter. And what you learn in the first day of the class is that information theoretically speaking, you can find a good predictor with, roughly speaking, order log f number of samples, right? And this logarithmic dependence is really important because, if you think about the effective size of function classes, they're usually exponential in number of parameters. So log f really says that the number of samples you need is proportional to the number of parameters. And this is a pretty straightforward to prove. The algorithm is just straightforward integral risk minimization, and your proof is just the application of Hardness inequality plus union bound. Okay. And this is info-theoretic because we're ignoring the difficulty of computation and optimization and assume that you can just minimize training error. Okay, so this is the 101 of supervised learning. So what I want is basically the analogy of that for RL or batch mode RL, right? So what can we can try to derive a cartoon result over here. So again, we'll have some data. So in this case, we'll be having state, action, reward, next state tuples from the MDP. Now define how they're generated in a minute. And this data set needs to be exploratory, as I said earlier. Again, this will be formalized later. And similarly, we'll have a function class f. Again, we're assuming that's finite. And one of these functions is the Q star, the function that we want to approximate. So we're really in this realizable setting. Okay. And the question again is, can we find a near optimal policy using order log f number of samples? Okay, so again, I'm omitting a lot of other parameters that are also important. For example, the epsilon delta usual pack parameters, and also horizon of the problem. But we'll see them in a more formal version of the problem statement. Okay, so this is a after we formally define it, this will be a well-posed question, and the answer is either yes or no. If yes, we should be able to give an algorithm and analysis. If it's no, then we should be able to give a lower bound or a hardness result. Okay, so but as far as I know, so far, our current knowledge of this question is that we just don't know. Okay, but I think that what we should know the answer to this question because this looks so basic and fundamental, and just as the supervised learning result is sort of forms the basis of the mansion of learning theory. I think we really need to understand this very well to have a solid basis for RL theory. Okay, so let me define things more precisely, right? So here I'm thinking of a Markov decision process as usual, and actually I'm thinking of an episodic one where in each episode for time step h equals 1, 2, 3, and so on and so forth, the agent repeatedly observes the state as h from a potentially very large set. And every round it chooses an action AH. And let's say for now, we assume that it's the action space is finite and small. And it received the reward from a reward function, R of SH AH. And then transitions to the next state randomly according to the transition dynamics of the system. Okay. And we'll be thinking about policies, right? So policies pi that maps states to actions. And for each policy, we're interested, the ultimate measure of its performance is defined as this J pi, which is the expected discounted return of this policy when we start from a particular initial state distribution nu 0, okay? And we're here, of course, gamma is a discount factor, and it roughly translates to a finite horizon of 1 over 1 minus gamma. And throughout this talk, I will be somewhat jump back and forth between the infinite horizon discounted setting and the finite horizon undiscounted setting. And because they're really similar and not that different, but ask questions if you're confused. So, and again, like mu zero is the initial state distribution, right? And just to quickly review concepts that should be familiar to everybody, we have this Q star value, which is the optimal value you can obtain if you start from a particular SA and follow the optimal policy afterwards. And optimal policy pi star is greedy with respect to Q star, and Q star satisfies this well-known Bellman equation. Okay. Assume this is all familiar for the audience, and I'm just quickly refreshing them. Okay, so now we come to our batch learning setting, right? So we now have a data set, and for simplicity, I'm just going to assume a very simple data generation protocol where you sample SAID from a what I call data distribution mu, a distribution over the state action space. And after you sample SA, you generate RNS prime according to the reward function and the dynamics of the MDP. Okay. And we'll have some condition on mu shortly. So again, we have a function class F. These are state action value functions. And we assume that one of them is Q star, or Q star is a member of this function class. And the entire goal of learning is to find a F, presumably inside the big F class, such that it induces an epsilon optimal greedy policy, right? And recall that whenever we say a policy is optimal or near optimal, whether it turns into the initial distribution, that is to the optimal. Okay. So now I have I can ask the earlier question again. Yes, go ahead.
Yeah, like your sound was breaking up, so whatever you were doing to make it happen, I guess you didn't do anything, but I guess maybe it's just good to take a pause so that the servers can catch up, and then you can continue. I guess.
Yeah.
Yeah, I think maybe you need to shoot down your second computer. Yeah.
Right.
Yeah.
Maybe the bandwidth, yeah, is overused.
I've look better now.
Oh, the sound is still pretty bad, breaking up.
Mm-hmm.
And the
yeah. Okay.
It's getting better, I think.
Okay. So let me know if something if things get really bad, and you know, I'll pause and see if I can do something. Okay, so
Okay, it sounds good now.
So now it's fine.
Yeah. Okay. So right. So now I want to ask the earlier question again. That is, you know, can we learn an F that induces a near optimal policy with a sample complexity that's polynomial in you know, the logarithmic size of the function class, horizon of the problem, and the usual epsilon delta, the usual pack parameters. Okay, so you know, because you know, value function approximation is such a fundamental topic in RL, there's a very large body of literature on this. We have some pretty decent understanding in this topic, and so according to what we know in the literature, the answer is yes, but we need two more assumptions, right? So the first assumption we need is to say that our data needs to be exploratory. And here exploratory roughly means that no policy will induce a distribution that is, you know, too different from your data distribution. And the other one is on the function class, right? So it turns out that we don't know any algorithm that can give you this polynomial sample complexity guarantee with just realizability. All of them need to assume something else. And one typical assumption you assume is to say, for example, the function class is closed under the Bellman update operator. Okay, so so in the rest of this talk, what I'm gonna do is to really look into these assumptions, see what they mean, and try to remove them and see if I can prove a exponential lower bound against learning, which will tell us that we really need these kind of assumptions, right? What we will start with is the first assumption, the data assumption. Okay, so what this assumption really says is that, if you think about mu as your data distribution, and then you also think about what's the distribution over state action pairs, or states sometimes, induced by any policy pi that you might be interested, and you compare these two distributions. And what you do is that you compute you define this number C, which is often referred to as concentrability coefficient, as a uniform upper bound on the density ratio between these two distributions, right? So you look at any state action pair where the density induced by a policy pi is high and the density of mu is low, and you say, what is the ratio between these two densities? The assumption here, when we say that the data is exploratory, what we're really saying is that the concentrability coefficient C is small. Or alternatively, in our sample complexity result, we allow ourselves polynomial dependence on C. Okay, and now you can ask, do we really need this assumption? And the answer is affirmative, right? So we can show that when C is unbounded, you can actually prove a exponential lower bound for any algorithm. So polynomial learning is impossible without this assumption. Well, it turns out that the story here is a little bit more complicated. Yes. Yes.
Nan,
go ahead.
Go ahead. Question on this one. So are you going to formally define concentrability coefficient and this lower bound in detail?
Let's see. I can give a more detailed definition of concentrability coefficient. I don't have a more precise definition in this slide, but the lower bound will be more, concrete. So, right. So the reason is because, in the literature, there are 10 or 20 different versions of concentrability coefficients. And if you want a canonical, or if you want a simple one, what you can think of is, pick any policy in MDP, pick any time step, look at the state action distribution induced by that policy at that time step, and then compare that distribution to your data distribution, right? Look at the largest, look at the maximum magnitude of the density ratio. That's going to be the concentrability coefficient. And there are many other environments that are sometimes tighter than this definition.
Right. Okay. Gotcha. Well, I guess I'm more curious about the lower bound, but I guess you're gonna get it, so I'll let you go on.
Okay. So, but if you think about this, the actual situation is a little bit trickier here, right? Because you don't need to be very clever at all to prove a lower bound if you just remove this assumption. Because what I can give you is a trivial lower bound, right? That I just give you a non-exploratory data. Right? For example, if my data set only consists of transition tuples that come from a single state action pair, of course, I'm not gonna be. I will not be able to learn anything from this data set. So, what you want to do is that you want to rule out this uninteresting failure mode, that the data distribution is chosen in a bad manner, and instead, what we can ask is, what if we allow the data distribution to be chosen favorably, right? So if we say we just choose the most exploratory data distribution, maybe for a family of problem instances, can we use that to replace this concentrability coefficient assumption? Okay, so that's the idea, right? So because one intuition is that you said that you need a data distribution to be exploratory. Okay, so I can try to give you the most exploratory data distribution I can think of, right? Should that satisfy the assumption automatically? Okay, so it turns out that in the worst case, that's not going to be sufficient. Okay, so there's still an exponential lower bound, even if the learner can pick the most exploratory data distribution. And here goes the lower bound. So you have this exponential tree MDP. This is a finite horizon one, but you can turn it into a discounted version. You have an exponential tree, and there's one leaf that gives you a little more reward than all the other leaves. And so without any side information, all you can do is basically try every leaf at least once. So you end up with exponential sample complexity. Okay, and we also want to make sure that you can construct a realizable f such that the logarithmic size of f does not explain away the exponential. And in this case, it's easy because there are just a to the h total problem instances in this problem family, and you just take each problem, take its q star, and collect all these functions into a bag, and that is your f. It's automatically realizable, and it has a polynomial logarithmic size. Okay, so, and we'll be talking about some other assumptions, for example, closeness under Bellman update. It turns out that all those assumptions can be satisfied similarly without giving you a very huge logarithmic size of f. Okay, and if you stop here, you will realize that if all I give you is this realizable function class and a random problem in this problem family, there is no algorithm that can efficiently explore if the algorithm has online access to the environment. Right, so this is the online setting instead of the batch setting, but we're going to connect back to the batch setting, like just in a second. Right, so one key realization here is that this construction in particular, all the problems in this family share exactly the same transition dynamics, and the transition dynamics are also deterministic, which means that if you have any data distribution in mind that you think is very exploratory or exploratory enough, and you want to apply a batch algorithm on this exploratory data distribution, their combination is just going to be a special case of an exploration algorithm, right? Because if you want to sample any state or state action pair, the exploration algorithm can just pick a particular sequence of actions to go to that state and sample the rewarded next state over there, right? Or up to maybe an overhead of a H factor. So what this really says is that.
So sorry, just to clarify, when you say that no efficient exploration algorithm exists, is that like a lower bound, or you're just saying that we don't know yet?
No, it's a lower bound, right?
You can solve this problem.
It's a lower bound because
right.
This is essentially just a multi-arm bandit with exponentially many arms, and the function class is uninformative. If you know the problem family, you can construct this function class yourself. You don't need me to tell you this function class. And it is well known in the multi-arm bandit literature that if you just have an unstructured multi-arm bandit that looks like this, where one of the random arms has higher rewards than all the others, then you must pay sample complexity that is at least linear in the number of arms. And here is the number of leaves. Yes.
All right. Okay. Gotcha. Perfect.
Right. So, and now we know that like pick your favorite data distribution in this problem, hook it up with any batch algorithm. It's just not going to work, right? So they are subject to the same exponential lower bound. Okay. So I think what this lower bound really tells you is that this assumption of low concentrability coefficient is not really just about data. It's as much as about data as much about data as it is about the MDP itself. Of course, it requires that the data to be exploratory, but at the same time, it also requires that when we talk about the density ratio between these two distributions, we're not really talking about two distributions. Because on the right-hand side, we're talking about distribution induced by any policy pi that you might be interested in, right? And if you have a large policy class and your MDP has complicated dynamics, we're talking about a lot of different distributions over here, right? So if those distributions differ too much from each other, basically what the lower bound says is that there's no single data distribution that can well cover all of them. So the low concentrability coefficient is also saying something about the net dynamics, and which I'm informally referring to as like smooth dynamics here. But here, smooth is a very big word. It should not be interpreted as related to like Lipschitz smoothness or anything like that. And if you want one canonical example of such smooth dynamics, I think you should one typical example I usually think of is large MDPs where the transition matrix, you put the transition probabilities into a SA by S matrix. When this matrix has a low rank stochastic factorization, it is easy to show, actually we show in the paper, that there always exists a data distribution that has small concentrability coefficient that is upper bounded by the rank of this matrix. Okay. One interesting side comment here, which I will come back to at the end, being the controversial part, is that oftentimes what we find is that similar structures also allow you to perform efficient exploration in the online RL setting when you also use the value function approximation. So looking at these kind of structures allows you to kind of compare batch learning, batch RL, and online RL in the function approximation setting, sort of side by side, and it has some like interesting implications. Again, I'll come back to this at the end of the talk. Okay, so I think what we have covered so far is to show you that by proving a lower bound, we can really confirm and reassure ourselves that we need something like this concentrability coefficient assumption on the data distribution, because if we, which is an assumption about the data and about the MDP dynamics, and if we remove it, we will not be able to achieve polynomial sample complexity. Okay, so it turns out that this part is relatively clear, and I think we have a pretty good understanding for now. To me, the more interesting and the more mysterious part is the second assumption, the assumption on the function class. This is where our understanding is still very much lacking, and we have many open problems here, and which I don't have answers to. And in the rest of this talk, I'll be going through. I'll be talking about mostly about this assumption. Okay. So before I talk about that assumption and why we might need it, let me just quickly review, a representative algorithm for batch RL. And in particular, we'll be thinking about fitted iteration, FQI, right? So just to remind you what FQI does, it initializes F0 arbitrarily from your function class. And in every iteration, it turns your RL data set, the SARS prime tuples, into a least square regression data set, where the features or the inputs are SA pairs, and the output is the empirical Bellman update based on the single data point. And this real valued label depends on your the functions from the previous iteration ft-1. And what you do is that you just run least square regression over your function class to fit f sub t as your next function, and just repeat this over and over again. And this is like a one-line, mathematical expression of the algorithm. And the intuition here is that if you look at this least square regression problem, the base optimal regressor here is literally the true Bellman update of ft-1. So if your function class is rich enough, and you can, you can predict this label very well, then you're doing an approximate Bellman update and mimicking value iteration. Okay. So what I'm next going to show you is that is some hints and some algorithm-specific counterexample that suggest why it is not enough to just have realizability, right? So what happens when we run our familiar algorithms when all we have is the function class that captures Q star, which is the function that we really want to approximate? Okay, so the example that I'm going to use here, again, is a finite horizon example, is a very, very simple chain MDP where you start from state number 1 and just deterministically transition to state 2, 3, 4, all the way to 10 or whatever. And there's no intermediate reward, and you just get a Bernoulli reward at the end. Okay. So and because there's no actions, your data set will look like something like state number 1, you get 0 reward, transition to state number 2, and so on and so forth. And at the end, from state number 10, you get a bunch of random 0 and 1s as your immediate rewards, and then the process terminates. Now, if you think about how fitted iteration, or in general, most of the approximate dynamic programming algorithms work in this problem, it's pretty straightforward, right? So at the end, you just average the reward you get, and you obtain some number, which should be close to the true expected reward 0.5. And you just use that as your learned value for state number 10. And for the previous states, what you do is that you do bootstrapping, right? So you say, I know state number 9 transition to state number 10. So probably state number 9 has a value that is 0, the immediate reward, plus my learned value of state number 10, right? So this is like the entire, learning, making a guess based on a guess, like the learning based on bootstrap targets. And by this, you learn that state number 9 has the same value, and so on and so forth. You just propagate this value all the way to the beginning. So nothing goes wrong in this case. And the reason is because we're using a tabular function class here. We're not really doing any function approximation, right? So in the function approximation land, you cannot express all the functions over the state space, right? So you can only express a very restricted subset of all the functions. So to mimic that, I'm going to literally do that. I'm going to take the same problem, but now I'm going to force you to predict only a limited number of values at each state to mimic the restriction of function approximation, right? So at the very end, I say, okay, for state number 10, all you can predict is either 0.5 or 0.501, okay? And at state number 9, you can also choose from these two values, number 8, and so on and so forth. And I'm doing this construction in a particular way where if you look at the values in the second row, the gap between the two rows is growing up exponentially as we move from bottom or from the end to the start. Okay, so now let's see how learning from bootstrap targets actually fail in this case, right? So as usual, you learn that the last state has a value, say 0.501, which is pretty close to the true value. Now you use that to form the bootstrap target for the previous time step. And now what you realize is that your label is slightly wrong, right? Because you're treating your learned value of state number 10 as if it were the true value, but it's not. And if you look at the predictions you're allowed to make in state number 9, which is either 0.5 or 0.502, they're equally distant to your slightly wrong label. So just by adversarial tie breaking, you may just randomly end up with 0.502, which is a little bit more wrong. But you can see how this is going, right? Because just by tie breaking, you can just end up with the second row as your prediction. And eventually you end up with a ridiculously large error at the initial state. And if you're, if you don't want these like actual numbers, you can totally replace them with these constructions, like these numbers over here, which essentially tells you that if you want to guarantee that your prediction at the initial state is epsilon accurate, you need to get the reward fitting at the end to be exponentially accurate, right? So essentially, you want your reward error at the end to have an error that is smaller than epsilon over 2 to the h. And we're talking about essentially policy evaluation here, but you can easily turn this into a policy optimization problem where this prediction error turns into a policy loss. And what I want to emphasize here is that, although I have restricted the possible values that you can predict, I'm still, the function class I give you is still perfectly realizable because the first row is the true Q star in this case, right? So what this really says is that if you just have Q star, if you just have realizability, learning based on bootstrap targets can have compounding errors that just blow up exponentially over time. Yeah, go ahead. Sorry.
Yeah. So just a quick question. So where is this exponential dependence coming from? Like, why can't it be like double exponential or whatever, right? Like, you didn't quite argue for that exponential is really what is sufficient or something, right?
Are saying that. What do you mean by sufficient? You mean
like if you would go up to an exponentially better accuracy at the end, the reward or whatnot, the value, then that would be sufficient at the beginning. Like, it's a little bit unclear, like why you bring up the exponential function. You could bring up any other function. This argument would still work.
Precisely what we have here is an accuracy that says if you literally run like FQI or basically any like one-step TD style algorithm, your sample complexity is lower bounded by 2 to the h. Right? I'm not saying that 2 to the h is generally sufficient, it is sufficient in this case, but I'm not making a general claim about, whether many of these ADP algorithms have a exponential sample complexity, like upper bound. Does that answer your question, Chaba, or you're asking something else? I feel like you're asking something else.
No. I think that in a way it answers the question. So you're saying that, like, if you put this together, that there exist algorithms whose sample complexity is exponentially in the horizon, then this kind of like like finishes up this question of whether the dependence on the horizon in the lack of extra assumptions on the function class could be exponential. And we know that it, like, the positive results tell you that it can be worse, and this tells you that it can be as bad as that.
Right.
Okay. But like you didn't quite explain why it can't be worse than exponential. That was my question.
I don't think we have a It might be. We don't have results for that. It might be, although I don't know. I don't know. Yeah. Can you? Well, but I think it's unlikely. I think it's like, for example, if you're really in a general finite horizon setting, I think you can get away with. If you are happy to pay an exponential dependence on horizon. I can't sketch a proof off the top of my mind now, but maybe we can discuss that later. But I think it should be possible. Okay, so we actually, this example is given with Chris Dan and others. Chris is over here today in our 2018 paper. But I want to point out that you can find actually in some sense similar conclusions and constructions maybe 2 decades ago, where people show that when you run ADP algorithms, even on a simple 2-state MDP with value function approximation, we just keep iterating, things will just blow up exponentially. In that case, like, the algorithm doesn't even converge, and it just predicts like larger and larger value. Okay. So now we're getting back to our assumption earlier, right? So how can you fix this situation with additional assumptions, right? So one thing you can do is you say, okay, so whatever prediction I'm allowed to make downstream, I want to be able to make the same predictions for earlier states. This will fix the problem, at least for this particular counterexample, right? And if you want to generalize it, basically what it says is that, because in infinite Q iteration, we're solving this particular regression problem, and we really want to do a good job in solving this regression problem, which means that our function class should contain the base optimal regressor for this problem. And because ft-1 can be random, we just make that a pessimistic assumption, which says that for any f in the class, its Bellman update t sub f is also in the tf is also in the class. And this assumption, the violation of this assumption is often known as the inherent Bellman errors, introduced by Chaba and Rumi around 2008. And if you look at what this assumption is saying, in the finite horizon setting, what it says is that you need to use richer and richer function classes at a lower level. When you're close to the beginning, when you're close to the starting point. And if you use a richer function class at a lower level, it is more difficult to satisfy realizability at higher levels. And in the discounted setting, what it tells you is that not only your function class has to capture Q star, but it is also required to be closed under the Bellman update operator. And this closeness assumption is not a monotone assumption, because adding new function to your function approximator actually hurt your approximation power according to this definition. So in this sense, I think it is this assumption is more or less undesired if you compare to what we have in supervised learning, where everything is like super straightforward. The richer your function class, the more representation power you have. So everything is very straightforward and intuitive, right? So, and I should say, if you are willing to make this assumption among a few other alternatives, you can totally get a sample complexity that is polynomial. Sorry, I realize I'm running out of time, so I'll go through the rest relatively fast. Okay. So an alternative perspective on the hardness is, this previous counterexample is really algorithm specific. It's specific to algorithms based on bootstrap targets. But it turns out that but it has a deterministic construction, which means that you can overcome. It's actually possible to overcome all the deterministic constructions using a different type of algorithms, which actually just directly estimate the Bellman error of your function and just try to minimize it. And you can do this very easily, like by just for example, tweaking a line of code from the DQN code. It actually works pretty well if you have deterministic problems. But the problem is that it actually completely breaks down if your environment has high stochasticity, because it has because this objective function has a second term that is just added to the first term, which is the Bellman error that you care about. And you can overcome this again with additional assumptions, but none of these assumptions are something that we have assumed in the previous setting. Okay, so basically this kind of suggests that it is not enough to just have realizability, right? So all the known algorithms that we have seen so far, they all require some additional representation assumptions in order to give you polynomial sample complexity guarantee. So I think this is a pretty strong indication that we should be able to prove a lower bound that says if all you have is a realizable function class, it's not going to be enough. There is still an exponential lower bound, exponential in horizon lower bound in terms of sample complexity. So this is what I'm conjecturing here. But turns out that this is surprisingly difficult to prove. And what I've tried are a few very general proof styles. And what I realized is that they just fail almost immediately. And the way that they fail are also kind of interesting. So I want to quickly go through them, hopefully in the next 5 or 10 minutes. Okay, so the first attempt is to say, how do you prove a information-theoretic lower bound in statistical learning theory? Well, the first thing you do is typically to construct a family of hard instances and let the nature chooses one adversarially from them for your algorithm. Okay, and if you have a exponentially large MDP instances, the natural way to construct your realizable function class is again just to collect their Q star value together. And what you want to show is that no algorithm can achieve polynomial sample complexity if they are given an adversarial instance in this family. And basically here, without any further tweaks or I don't need, if you go down this route, you don't even need to show me your construction, and I can tell you that you've already failed. Okay, so in this particular setup, there exists actually an info-theoretic algorithm that does achieve polynomial sample complexity. And roughly speaking, what it does is that it takes the family of MDP instances and it can create an F prime that is closed under Bellman update and is only slightly bigger than the realizable function class. And so the actual issue here is that our setup, when you prove a algorithm agnostic lower bound, you don't want to put any restriction on your algorithm. But that turns out to be the wrong thing to do here, because if you don't put any restriction here, your algorithm can be model-based. And if the algorithm is model-based, it can actually overcome all these difficulties related to bootstrap targets, failure, difficulty of estimating the Bellman error, and so on and so forth. That is only there for value-based RL algorithms. So we actually need a mechanism to separate between model-based RL and value-based RL in order to prove this lower bound. So I'll skip that here. So what can be one such mechanism, right? So it turns out there's one mechanism that we have used before. It's also hinted in the new edition of the Sutton and Bartle textbook. That is, you mask your data. Okay, so if you give me your data set as a RS prime, what I'm going to do is that I'm not going to let the learner see the state directly, but the learner can only query the value of any function f evaluated on the state in the value function class. And we call this the value profile of a state. And in the linear setting, if you do linear function approximation, this basically amounts to revealing the state features to the learner, which is what Sutton and Bartle did. And what this can do for you is that it can induce state aliasing. It can confuse the learner of two states that are actually different, but they can have the same value profile. And this mechanism is also general. It's a restriction, but it's a very mild restriction that is general enough to allow most known value-based methods. Okay, and actually, Sutton and Bartle have shown that you can actually have very small and tabular construction where even with infinite amount of data, the learner, no algorithm can learn the Bellman error of actually a function that is not Q star. Okay, so, and I can refer you to the precise chapter of the book. But when I first see this result, I feel like it's very, very promising because, finding Q star is closely related to minimizing the Bellman error of a function. So if they can show that you cannot learn the Bellman error, it seems like this is only one step away from proving that, we cannot learn Q star. But the sad news is that as I tried that a little bit, I realized that if you take their construction and you add realizability to it, then everything is good. All the hardness is gone. In the tabular setting, if you give me a realizable function class and you mask the data with value profiles, I can still achieve polynomial sample complexity. And roughly the reason is that I can just treat the states that have the same profile as if they were the same states. This induces a particular type of state abstractions called Q star relevant abstractions. And you just run model-based algorithm on the state space, and it's going to give you, it will learn Q star with very reasonable amount of data. Okay, so sorry that I've rushed through this, the last part of the technical slides. So I want to wrap up a little bit here by saying why I care about this hardness conjecture, right? So here, what I'm putting here is sort of different settings of RL. Batch versus online, value-based versus model-based. For RL to work in any of these settings, roughly speaking, we all need two kinds of assumptions. One assumption on the MDP dynamics to be structured and smooth enough. And in the batch setting, you also need exploratory data. And the other assumption is on the your representation power. So if you look at these quadrants, you can start to make comparisons between different modes of RL and draw interesting implications. For example, if the batch learning setting really requires much more than just realizability, then at least in some cases, we can say that the online exploration setting may be easier than the batch learning setting because, for example, in these low rank MDP setting, we know that you can achieve polynomial sample complexity in the online exploration setting with just the realizability alone. Okay, we don't need like low inherent Bellman error or any additional assumptions. This is a pretty surprising finding that we have in our 2017 paper, where we proposed the low Bellman rank stuff. And if the hardness conjecture is true, it also says something of the gap between batch mode value-based RL and batch mode model-based RL, right? So that's why I think this construction, this lower bound itself is interesting. And it's also interesting for a different reason, that its construction is going to be highly different from all the lower bound constructions we have so far in the RL literature. Because all the construction we have so far essentially have a banded structure. And none of them really reflect the interesting and challenging scenarios of RL where you have multi-step decision-making with stochastic transitions, and you get informative intermediate feedback signals. In all the constructions we know, the intermediate state you see are just uninformative. You know them in advance. For the nature, the system tells you which state you're in, okay? So that's why I think like not only the lower bound statement will be interesting, but the proof itself will be also very interesting because it reflects this very interesting challenges and also related to other require of very similar flavor. So this is of my talk, and thanks everyone for attending, and sorry for rushing through the last part of the talk.
Thank you very much. I don't know about the others, but I didn't quite catch the very last connection, I suppose. I mean, I'm certainly very inspired by this talk that really highlights lower bounds and negative results, which are typically the results that get buried deep into the appendix of some paper. I think it's very nice that you present it to all of us. Let's see if anybody has any questions.
Robin had a question.
Hi, yeah, can I ask one? Nan, thank you so much for your talk, and I'll be talking to you this Friday. This is Robin from TalkRL.
Yeah.
So as you, hi, so I'm very poor with theory, so I apologize for my questions. But my question is, can this exponential explosion of error maybe explain why distributional RL does better?
Yeah, I think that's a very good question. So I thought answer. If you think about
Nan, gotta stop. Just stop a little bit and wait. Your sound is breaking up. I guess when you're moving, the camera is, like playing games here, but it's not enough for both the camera and the sound.
I see.
If you're deactivating the video, then that helps, except that we won't see you, but maybe that's...
Yeah, I mean, I can... turn off the camera for a minute.
Okay,
Does my sound sound better?
I think so.
A lot better. Yeah.
Yeah. Okay. So so I think when I think about how distributional RL fit into this picture, I typically think of the last part of the talk where I talk about this value profile sort of mechanism, right? As a general definition for a value-based algorithm, right? So basically, when you have different algorithms, they sort of exploit different amount of knowledge in states, right? So if you have a purely value-based algorithm, they sort of only access states by passing your states through your value function approximator, right? Whereas in distributional RL, I think of distributional RL as somewhere in between value-based RL and model-based RL, right? Because it models more than just the expected value of long-term return, but it also models less than the full transition dynamics. So somewhere in between. And to the point that we know that in the results that I presented, that if you're doing full model-based RL, you can just get away with model realizability. And when you do value-based RL, it seems that there's a hardness result. Then it shouldn't be too surprising if distribution RL is somewhere in between that may or may not be able to overcome the hardness result of value-based RL.
Thank you.
All right, Nan. So can I have a question regarding your terminology on this last slide?
Yes, go ahead.
On the previous one, that is.
Yes,
that,
go ahead.
it's for
I realize it's
I'm just,
very vague. Yeah.
Yeah, I'm just trying to understand, for example, in the lower left corner, where you say that smooth dynamics and realizability is enough for what precisely? Information-theoretic learnability? What do you think about efficient learning in that setting? Are these assumptions enough for that?
I'm referring just to polynomial sample complexity.
Right, and how do you think this picture would look if you also thought about computational efficiency as well?
Oh man, no, I don't know.
Right.
The fact that we repeatedly run into computational difficulties, in that 2017 work and afterwards, I think it also suggests some kind of I would say there might be some hardness if you consider computation and statistical efficiency together. For example, in optimization and in supervised learning, there's these statistical computational trade-off that says if you're only happy to spend this amount of computation, you can't get the best statistical rate, right? So something might be true here, but we don't know. All we know so far is that the algorithm we had for in that 2017 paper for low Bellman rank, that one is truly in a follow-up paper with Christian, we showed that it's at least it's not oracle efficient. Even if you have all the usual NP-hard oracles from supervised learning, you cannot implement the computation in polynomial time.
I mean, you cannot, or every algorithm that you could think of so far would not work.
Well, the thing is that if you're in the online setting, we don't know that many algorithms that give you polynomial sample complexity just with realizability. I think most of them, again, similar to the batch setting, require additional assumptions, right? For example, I think, was it Shijing or someone else talked about, linear function approximation in this linear MDP setting, right? So there, you're not only making the linear value function assumption, but you're also assuming something pretty strong about the MDP dynamics to the point that, to the extent that the linear function class has 0 inherent Bellman error, right?
Right. Yeah. So that already
and
implies,
there you get both computational and statistical efficiency.
Yeah. Right. Yeah. So I guess that's what I was getting at, right? So far it seems that this smooth dynamics and realizability is not really enough for that setting. But if you add this very strong realizability, which implies 0 inherent Bellman error, then you can get. Let's see as well. All right. So there was a question by Anirudh Mula. He's saying that his microphone is not working, so I'm gonna read his question, which goes as follows. So is there a gap between batch value-based RL and batch model-based RL? And what sort of assumptions do we need to? What sort of assumptions do we need for a function class used to approximate the model in model-based RL? That's his question.
I think my second to last slide, I think what I'm saying there is that we don't have a proven gap between batch value-based RL and batch model-based RL, right? Precisely because we don't have this hardness conjecture proved. And for some people, like even if I prove that conjecture, they would argue that I'm not comparing value-based and model-based RL like in a fair way, right? Because model-based RL gets model realizability, which is in some sense much stronger than just the value realizability. But I think I would argue is, if you think in the information theoretical mode kind of way, these realizability assumptions are in some sense what it means to have value-based and model-based algorithms. I have Amir Masood has a question that I like a lot. Do these conclusions also hold for the policy evaluation problem? Great question. So, Amir apparently and Chava, you guys are experts on this matter, and I did my PhD like reading your papers. So yes, I mean all the majority of the difficulties I talked about today, right? So what I focused on is the difficulty of bootstrapping related to bootstrap targets, and also the difficulty. The other one that I slightly touched on is the difficulty related to estimating Bellman error in a stochastic environment, right? So both of them are still there, even if you don't think of policy optimization, but just think of policy evaluation, right? So this makes us, I think it is attempting to conclude that we may have similar hardness, even if we just think of policy evaluation, right? I give you exploratory data. I give you a value function class. One of them is vpi or qpi, whatever. I ask you to tell me to estimate jpi. Can you do that, or can you not? But what makes me slightly, and when I wrote this paper, I think my belief is that things are similarly hard for policy evaluation. But for now, my belief has shaken a little bit, I have to be honest, precisely because I've been recently working on these minimax of policy evaluation methods. I've been thinking about how can you maybe get away with some of the assumptions. So for example, I can tell you one result that the literature already that's already there in the literature. If you have linear function approximation in the off-policy evaluation setting, and you can run LSTDQ and use that to estimate jpi, right? So it seems like you can almost just estimate jpi accurately with a realizable linear value function class. There's some trickiness about the data distribution. There's some additional requirement on the data distribution, but those requirement and assumptions do not seem as strong as something like low inherent Bellman error. So that's what made me think maybe policy evaluation is a simpler problem than policy optimization in the batch setting. We don't know. We're actually actively working on that. Right.
Okay, great. Thank you. Hi, this is Amir Masoud. Just want to say, well, great talk. I enjoyed it. And so maybe just add a little bit about why I asked that question. I guess one of the reasons is that if policy evaluations happens to be much simpler, then I'm thinking about the relation of the recent results for policy gradients. Essentially think about actor-critic type of method. If critic happens to be easy to learn, then we have convergence results or for the actor part, like policy gradient part of it. I mean, the results are not complete. I mean, I don't think they're necessary for full actor-critic, but still, I mean, this is not completely value-based, but it would be something in between.
Right.
So that's, I guess, one thing I was thinking about. And maybe one other comment about that's, I mean, about the assumption of whether the function, say Q star belongs to the function space or not. So I think what Csaba and Remy have, like this inherent Bellman error, seems to be, I mean, capturing it, but it is too conservative. And I'm thinking that it is actually not needed. Like maybe the assumption of realizability, maybe that's too weak, but also inherent Bellman error being 0
is too strong.
But
I mean, so there's definitely a, you have done these kind of proofs like numerous times. So we all know that you can relax it to something like all you need is that you need those assumptions to be satisfied for the sequence of functions that you actually encounter along the way, right? And inherent Bellman error is basically a pessimistic version that relaxes it to a priori statement that doesn't depend on the randomness of execution. Do you think when you say you can get a weaker condition, do you mean something even weaker than like requiring that on the actual path sequence of functions you encounter, or that's what you mean?
No, that's exactly what I meant. So I don't know if something weaker than that exists or not, but just the path of functions that we construct, if all of them exist, then that should be enough.
Yes. Although, I mean, like, depending on your personal taste and style, like, I always want a, sort of a priori bound. So then I need to go back to inherent Bellman error, right? Unless we have some way to sort of control and predict the behavior of the algorithm that it's only gonna hit like these value functions or something like that. Unless we have a fine-grained characterization like that, then I think we just get stuck with this inherent Bellman errors.
Right. Yeah, that's true. Okay. Thank you.
Thank you.
So I have another question related to this one, which is so all these arguments that you had in this talk were really based on somehow the fact that if you're working with a function class, then you have to reason about this inherent Bellman error, sort of, right? Which means that you're implicitly making the assumption that you have to bootstrap in order to work with these function classes. But do you think that's actually true? Can you come up with algorithms that do not need to bootstrap and would be able to get away with that?
So yeah, I think that's a very good question. I mean, again, I did a very poor time management, so there are actually quite a few slides where I hinted at some of our recent development that studies algorithms that do not require bootstrapping, right? So this is again like For example, in our, I have a recent UAI paper with my student Yang Xie. We analyze the algorithms that has this minimax style that actually tries to directly estimate the what I call average Bellman errors instead of the squared pointwise Bellman errors, right?
Oh,
so
yeah, right.
What you do is that you can employ a marginalized importance weights class to mimic different distributions that you might encounter when you roll out your learn policy, and try to learn a Q function that has 0 average Bellman error on all these like counterfactual distributions, right? So you can show that as long as your learn policy induces a distribution that is captured by one of your marginalized importance weights, or actually just a linear combination of your importance weights class, then you can also give a polynomial sample complexity guarantee. But the thing is that here now you need additional marginalized importance weights class, right? So we don't have any algorithm that just work with a single value function class that's just realizable and nothing else.
Right. Yeah, I hear you.
Can I ask a related question? So I had one question.
Sure. Go ahead. Yeah. Yeah.
First, thanks for a really thoughtful talk. Okay, so I guess related to that question, one thing I've never fully understood is that it seems that in the approximate linear programming approach to approximate dynamic programming, there's it doesn't have these kind of closeness assumptions on of value functions. So I don't think it fits within your assumption of kind of learning from a single stream of data.
Yes.
I'm wondering if you've kind of thought about, I mean, maybe not, but if you thought about that particular algorithm and have any idea why, or if the closeness assumption is hidden somehow.
Okay, Chava echoes with your question. I think I have 2 thoughts related to your question. So first, as you said, it's not a single path algorithm. When you write down, for example, the primal form, when you write down the primal form, you need to use the actual Bellman update operator, right? Which I think, I mean, my guess is that then you get away with just the realizability because you're essentially doing something like the double sampling stuff, right? I mean, I skipped this part in my slides. Like, if I have access to double sampling, then I immediately just get polynomial sample complexity with realizability, because now I can directly estimate the Bellman errors, right? So that's one thought. The other thought is that this actually ties back to what I was telling Gergel just in the previous question about these recent minimax algorithms. Those algorithms are actually like heavily inspired by the linear programming formulation of MDPs, right? Because if you take the linear program formulation, the primal program, you take its dual, what you get is its dual LP has this constraints that looks like Bellman equation for distributions, right? So your distributions satisfy this Bellman equation as if you take a state from a discounted occupancy, evolve it for one time step, its marginal differs from the original one by the initial state distribution, right? Something like that. But then but yes, so if you look at some of the results in the literature, they do have algorithms that only require very weak realizability, or require only realizability type assumptions, which I agree, I myself haven't really well understood why that's the case. And I'll give one example. I think this is by Mondi Wang, Li Hong Li, and maybe one other author. It's called bilinear pi learning with state action features or something. And if I remember, they have some pretty funky data generation protocols. I think that plays a lot of role there. But eventually, their representation assumption says that all you need to be able to do is to linearly approximate your value function and linearly approximate the distribution induced by the optimal policy.
Nan, I'm going to have some controversial comments about that, but maybe like after.
Go ahead. No, that's the end of my response to this. I mean, that just seems like, that itself just seems like too good to be true when I saw it at the first glance. But Gergo, you have something to say about that?
It's way too controversial, so maybe let's just call this an end. Stop the recording, and I can continue this discussion.